as I mentioned earlier, today is a review session, so what do you want to talk about?
How is the test going to be formatted?
How is the test going to be formatted? Okay, so I'm not entirely sure what you mean by that specific question. So I'm going to tell you what you should expect. Is that what you were actually asking for? Okay. So it's going to look a lot like homework set number 5 and homework set number 6, because that's what I expect you to be able to do to take this test. So I expect to have one problem that will have, let's say, 2 to 3 functions in the time domain, and you need to be able to take the Laplace transform of those functions using the table. I'm going to provide you with the full table as your equation sheet for this exam. So on one side, it'll be all of the Laplace transform pairs. On the opposite side, it will be all of the properties of the Laplace transform and all that kind of stuff. So everything that you need to be able to do should be on that. I don't anticipate, well, let me say it this way. I'm not going to give you anything that you will specifically need to use the integral definition for the Laplace transform for. So you should be able to just use the table and the properties in order to figure stuff out. The second problem will be 2 to 3 functions in the S domain, and you need to be able to take the inverse Laplace transform of those. And then I haven't decided on whether it's going to be 2 or 3 simple circuits for you to analyze. The expectation is that you would analyze those circuits in the S domain and be able to do partial fraction expansion and find a time domain quantity without having to use MathCAD or anything like that, because you obviously don't get to use a computer for the in-class portion of the test. I know, I'm such a jerk. So that's what I expect the format, so to speak, to be for the exam. So 15-ish points for just straight math. Can you do the Laplace transform of these functions? 15-ish points for straight math. Can you do the inverse Laplace transform of these functions? That gives me 45 other points to play around with. So maybe 3 15-point circuits, or maybe 2 circuits, one worth 20 points, the other one worth 25, something in there. Anything sound unreasonable about that? Okay. For the take-home portion of your exam, I think I'm just going to give you guys 2 circuits, very similar to homework 6, problems 3 and 4, that would require you to actually use MathCAD in order to get your transfer function and all that kind of good stuff. And then that'll be it. Anything sounds unfair or you feel unprepared for?
We expect that you'll fail.
I probably wouldn't give you an op-amp, or let me rephrase that. I won't give you an op-amp circuit on the in-class portion of the test. I may decide to give you an op-amp circuit for the take-home portion of the test. Okay. Particularly, not that it matters, because you're going to have a damn near a week to do it anyway. But I had mentioned, for those of you that had me for circuits 2, when we covered integrators, I believe I had specifically mentioned that for a real op-amp integrator, you would usually put a resistance in parallel with your capacitor in the feedback loop in order to ensure that your system had no stored energy, so that we wouldn't have to like fudge the math to make it work right as an integrator. So one potential question that I've been thinking about would have you guys analyze that circuit in the S domain to show that the response of that would be an integrator, even with that resistor in the feedback loop with the capacitor. I don't know if I'm going to do that, but that's something that I've considered. Yes.
Are we allowed to use properties that aren't like ones that we know?
Which specific properties are you thinking about? So let me state something here. So like homework set number 5, problem 1E, I actually threw that problem out because I realized I did not teach you guys the frequency differentiation property of the Laplace transform. So like in the time domain differentiation winds up you're multiplying your f of s function by s. Well, going in the opposite direction, you would just, if you had a function in time, or actually, let me rephrase that. Taking the derivative of a function in the S domain is the same thing as multiplying it by t in the time domain. And so that would have been a much easier way to work homework set 5, problem 1E, but because I didn't teach that, the only other way I could think of you doing it was just actually doing the integral, which is an absolute nightmare. And so I was just like, I don't want to read through all that math of integration by parts, I think 4 times. So let's just throw it out and say that you did it. I'm not necessarily opposed to it, but I don't think it would be necessary. If you're going to use a property that I didn't give you, you want to be very explicit about what you're doing so that the work can be followed, I guess. So cover your ass. That sound fair? Yeah. Yeah. So I shouldn't, I don't intend to give you anything like that will require you to use that one, like the arguably easy way to do homework 5 1E was, which still isn't particularly easy because you would be doing a third derivative of that terrible thing. Yeah, yeah. Hot mess of bullshit. So, yeah. Yep. What I get for just pulling random problems out of a textbook and not thinking about them in context of what I've taught. So means next year I have to just teach that so I can make you do it, or make the underclassmen do it. What else? Yes, ma'am. Sure. Like just a generic example, or? I have not made the exam yet, so anything is close or anything is infinitely far away. Yeah. Okay. So. All right, so let me just make up a problem with some switches in it, then I guess would be the easiest way for me to wrap my head around representing that. So I think, Gavin, you were asking about this. So does this meet the criteria of a circuit you would be talking about in as much as the 10 volt source? Thank you, robot. The 10 volt source is being switched out at t is equal to 0, and 2 amp source is being switched in. That's okay.
That's similar, like we had on 2 unit step function, like you have negative t, it would be the source to the separate signal.
Yeah, so so if we have u at negative t, it's saying it's applying some voltage or current up until time t is equal to 0, and then it gets switched out, and then another source would be turned on. So like I think some of the things that I might have given you on the homework would have been let's just call it y of t is equal to, wasn't there one that was like 20u of negative t plus 20e to the minus, I don't know, let's say 5t u of t volts. Is that actually what you're asking about? Okay, well then let's get rid of some of this dumb shit. We don't need all this other crap on. We could have, but that would have just been one unit step function on the left side of the circuit being replaced by a unit step function on the right hand side of the circuit, which it is what it is. All right. So let's make y of t a voltage. Let's call this voltage Vs of t. And let's get rid of this dumb switch and just have it connected. All right, what quantity are we looking for here? Inductor current, inductor voltage, resistor current, resistor voltage, capacitor current, capacitor voltage. Capacitor voltage, okay? Is it okay that I put the positive polarity terminal on the left? That won't really matter. It'll just change the answer from positive to negative if we switch things. All right, so for a circuit like this, because we have something going on for negative values of time, and it's a constant for all negative values of time, we are going to analyze effectively a DC circuit with its voltage source looking like a 20-volt source, right? So for t less than 0, let's call it less than or equal to 0 minus. This circuit looks like this, where we have a 20-volt source connected to a 5-ohm resistor. This is VC at 0 minus. So I already put the negative polarity terminal there. Okay. And even though we aren't specifically asked to solve for this, we obviously need to know what the initial condition on the inductor current is going to be as well, so that we know what our S domain circuit will look like for t greater than 0. Okay. So hopefully everybody can see very easily for this particular example that VC of 0 minus is 20 volts. And IL of 0 minus must be 0 amps. Really, really hope that at this point in circuits 3, you all agree with that. All right. So, assuming we're all in agreement there, for t greater than or equal to 0 plus, I'm just going to go straight into the S domain. So this would look like 20 over S plus 5. My resistor is still a 5-ohm resistor. I'm going to have my capacitor here. That's going to look like, let's see, 1 over 10 over S, right? So it was 0.1, so 1 over SC is just going to look like 10 over S. Does that sound right? Okay. My voltage source is going to be 20 over S. And then my inductor is just going to look like, I need to actually draw the damn thing. L was 2 Henry, so let's just call this 2S. And our goal here would be to find VC as a function of S. So before we start doing any analysis to this thing, is this what the circuit would look like in the S domain? Yes, Brody.
Your voltage source of the capacitor, is it plus on the left because of your terminals of DC?
Yes. So the positive polarity terminal should be facing the positive polarity terminal of the overall voltage for the inductor, or excuse me, for the capacitor. For the inductor, it would be the opposite. I believe that should bear out with what we talked about when we did the equivalent circuits in the S domain for capacitors and inductors.
Conductor, transformation, you just have it in parallel with the current source, which is 0.
So because my initial condition on it is 0, I'm not going to have a voltage source or a current source. If the initial condition were non-zero, I could choose to represent it with a voltage source in series or a current source in parallel. Gabriel.
So why do you not? Wait, the current source in parallel is.
For the inductor, well, the current source will always be in parallel. Right, but because it's, my initial condition is 0, it's going to look like a short circuit either way.
I thought it was like.
Or a short circuit in series or an open circuit in parallel.
Yeah, that's what.
Yeah. Daniel.
Is there any chance we can get the transformer for the capacitor and inductor for, main on the trading anywhere?
Send me an email to remind me to put it on there, and then sure, I don't have a problem with that. The question was, could I put the S domain representation of capacitors and inductors on the equation sheet for you guys? And the short answer to that is sure. Yes, ma'am.
Initial condition for the inductor was 5 amps up.
So I could choose to represent it as a voltage source in series with that inductor, having a value of 5 amps times L, where it would have been negative polarity on top, because the current would be flowing into the negative polarity terminal, or it would be a current source in parallel, where it would have been 5 amps over S direction down. I would just use whichever one would wind up making the math easier for me, which would probably be the series connection, I would think. All right, any other questions about setting this thing up, or can we actually analyze it?
Yeah.
All right, so how would you guys choose to analyze this thing? Killing me.
Source on the left with the resistor and then point everything.
Yeah, so that would be an easy way to do it. Source transformation for the practical voltage source on the left, so that you'd have a single loop circuit. That seems pretty easy. I was just thinking about the fact that the 20 over S plus 5 volts is between here and here. So effectively, we could just use Kirchhoff's voltage law around this loop to find the current, and then use that current to find the voltage drop over just the capacitor portion and add them together, which is actually going to get us the exact same result as if we've done the source transformation and done the same thing. Yes.
How do you source transform the left side? If it's
The exact same rules as the normal source transformation.
It had to be a voltage source in series.
Oh, you are correct. You're 100% correct there, yes. So we can't source transform this thing because it's not a current source in parallel. Thank you for that, yes. So that takes that off the table. So I think the other method then is probably the way that I would do it. So I'm just going to recognize, thank you for catching that mistake, that the potential difference between here and here is just 20 over S plus 5, right? So applying Kirchhoff's voltage law, we would have negative 20 over S plus 5. I'm going to call this current I of S plus 10 over S times I of S plus 20 over S plus 2S times I of S is equal to 0. Let's do a little bit of algebra here. So 10 over S plus 2S times I of S will be equal to 20 over S plus 5 minus 20 over S. Let's let me think about how I would pretty this stuff up. Now, obviously, over here on the right-hand side, I would multiply this by S over S, multiply this over S plus 5 over S plus 5, make that look nicer. I'm trying to decide if I would wind up multiplying the whole thing through by another factor of S to get rid of this S in the denominator here so that I can get it in a simple polynomial form. That's what I'm leaning towards, right? So let me think about this. So we would have 10 plus 2S squared times I of S will be equal to 20S squared divided by S times S plus 5 minus 20S times S plus 5 over, and my S's and my 5s are looking too similar for my comfort. S times S plus 5. Let me double check the algebra here because I'm doing it in front of you, which terrifies me. So what I've done is I multiplied this fraction right here by S over S. And then this fraction right here by S plus 5 over S plus 5. And then I multiplied both sides of the equation by a factor of S to get rid of this one down here. So that's why I have an S squared here. So this is multiplying by this S as well as multiplying by an S to get rid of this thing. This is just me coming up with a common denominator. And then this guy right here, the S right here is for multiplying through S to clear that fraction. And then I've got the S plus 5 over S plus 5. Let's now
Could that be an S squared? Second fraction.
I don't think it should. Okay, so let me explain why. Oh, but I can factor out S's all damn day here. That'll make it a little bit easier. So the S by itself in the numerator comes from me multiplying both sides by S to clear this fraction. The S plus 5 comes from me multiplying just this guy by S plus 5 over S plus 5. So I very strongly feel that it should only be a single S here. Okay. Now let's cancel out some S's to make life better. So this is going to cancel this. That's going to give me that. So I'll just have, let's expand some things out here. So that's going to look like 20S minus 20S minus 100. These guys cancel each other out over S plus 5. Are we okay to this point? I of S would then be negative 100 over S plus 5 divided by 10 plus 2S squared, which is going to look like negative 100 divided by S plus 5 times 2S squared plus 10, or negative 50 over S plus 5 times S squared plus 5. Algebra Working out okay here? Anybody got any beef? VC of S would then be my impedance, so 10 over S times IS let me look at the polarity of this thing, plus 20 over S. And then making this thing less ugly, that would be negative 500 over S times S plus 5 times S squared plus 5 plus 20 times S plus 5 times S squared plus 5, all divided by S times S plus 5 times S squared plus 5, allowing me to express this whole thing as 20 times S plus 5 S squared plus 5 minus 500 divided by S times S plus 5 times S squared plus 5. I would then do partial fraction expansion for this thing. So that would look like A1 over S plus A2 over S plus 5. Plus B, which is going to be a complex number, over S plus J square root of 5 plus B conjugate over S minus J square root of 5. That's how I would factor S squared plus 5. Anybody got a beef with that? The voltage drop across the capacitor is defined between here and here. So it has to include the voltage drop across this impedance plus the initial condition. And then I would solve for these coefficients. Do I need to actually do that? Or at this point, are we good to go? Yes, ma'am. The inverse Laplace transform, but yes. So we are going to have something that is a unit step function, something that is e to the -5. And in this business over here, it's going to look, so we're going to have some number. We have I think it's going to be a sine function. Could be a cosine. Well, actually, realistically, you would put this just as a heads up thing here. Think about this as S plus 0 plus J square root of 5, right? Which means the inverse Laplace transform that you would traditionally get here would be e to the -AT times cosine blah, 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 plus some phase angle. E to the 0 is just going to look like 1. So you're not going to have the exponentially decaying portion of that sinusoidal function. You're just going to have the oscillating part. I was trying to think about whether or not, and I don't know whether or not this would be valid, literally just leaving this as a term with S squared here because the inverse Laplace transform of 5 over s squared plus 5 would be the sine, the cosine of square root of 5t. But I'm not sure if I can leave a factor with a squared term in the denominator like that and it still work out the correct way. So I would probably full on do it this way. And then use that, one of the last identities that we dealt with to put this in terms of e to the 0t cosine square root of 5t plus a phase angle. Just to cover my butt would be how I would approach it. What else?
Example, would there not be in the trig function there, whichever one it is, there wouldn't be any phase angle because they cancel out.
There may be, I don't know, we would have to figure it out. If I had to venture a guess though, my best guess would be the phase angle would be either 0 or plus or minus 90. Yep. Just based entirely on the fact that my A term is 0, I think it would work out that way. Can't guarantee that, but I think it would work out that way. What else? Define easy. All right. No, let's do a capacitor here just for the sake of argument. 0.4 Henry, maybe. And Farad, thank you. Let's say that IS of t is 3e to the negative 2t u of t. Vs of t is just 10 u of t. So that we don't have any initial conditions because I don't want to make this harder than it needs to be. In the S domain, then we would have 3 over S plus 2, 10 S 10/4 would be 2.5 over S. Ten over S. IL of S. All right, so before we take a crack at this thing, is this S domain representation correct? Okay. So doing nodal, but not with MathCAD, which is why I made the circuit look like this, because it's the only thing I could really think of that would facilitate that. I'm going to choose this node to be my ground, and I'm just going to call this voltage Vx of S. And so we would have Vx of S minus 3 over S plus 2 divided by 10 plus Vx over S divided by S plus Vx of S minus 10 over S divided by 2.5 over S is equal to 0. Yep. Oh, you're right, because that's totally a current source. Thank you. 100% correct. Thank you for that, Brody. Mistake on my part. Negative 3 over S plus 2. Thank you very much. From here, we would just do algebra to solve for Vx of S. So let me think about some things. Those guys would cancel each other out. So we could literally just call this thing right here 4. So that would be that thing. And then how do we pretty up the other side? For this one over here, yeah, we could write that as S over 2.5. Let's do it that way, yeah. So let's play around with this thing really quick. So 1 over S plus S over 2.5 would look like 2.5 over 2.5 S plus S squared over 2.5 S would be S squared plus 2.5 over 2.5 S. I do my algebra correct? So pointing out that 1 over this thing is just going to be the reciprocal. Then I multiply by 2.5 over 2.5 over here. And then S over here to give me a common denominator for both of those. And then added things together. Now, because I am about to, let's see, divide this side by this thing, that will be the same as multiplying this by the reciprocal. So Vx of S would be 3 plus 4 times S plus 2 divided by S plus 2 multiplied by S squared plus 2.5. No, sorry, 2.5 S divided by S squared plus 2.5. Ba, 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 ba. So let's see. 4s plus 8 plus 3, so 4s plus 11 times 2.5s divided by s plus 2 times s squared plus 2.5. IL of s is just going to be bx divided by s, which would be 4s plus 11, 2.5s over s times s plus 2, s squared plus 2.5, and then we would partial fraction expansion that guy, and we're off to the races. Is that something like you were asking about? Assuming my algebra is correct, which could very well be a large assumption here, that's how it would work. Seeing how long it's taking me to get to this point on these simple problems, I'm definitely leaning much more towards only 2 circuits for you guys to analyze on the in-class portions of the test. And I'm mildly concerned about 2. So. Point values might be adjusted. It might be 1 medium difficulty circuit and then maybe 3 on the take-home test or something like that to kind of make things up, where you have more time to do things. Yes.
Is there a good source to get simple circuit like this practice other than the
Download literally any circuit analysis textbook, either legally or illegally. I don't know. It's not my business. And then just burn through examples. Practically any circuit analysis textbook should have some stuff on circuit analysis in the S domain. For what it's worth, the circuits that I gave you for your homework and all that kind of jazz came from circuit analysis and design by Fawaz T. Ulabi, the one that I recommended to you guys, and then I changed the input voltage signal or whatever so that you can't just Google it and get the answer. I mean, kinda.
well, number else if it's one only
And steady state analysis might have multiple inductors and capacitors. And then Daniel's right, just throw a U of T in there and call it a damn day. That's a circuit to analyze. That's how I came up with this. I was just thinking, what is something that I could do in the steady state sinusoidal domain without using MathCAD to solve? And then I just used time domain functions that have Laplace transforms. All right. Yes, Gabriel. You should be able to, yeah. If you can figure out how to make the sources behave the correct way, sure. Because it should have the transient, like if you did a transient response, it should have all of the extra stuff in there as well. Because we're no longer just saying wait until the transient dies out. We specifically want to know what's happening during the transient condition. What else? All right. I'll be in my office if anybody needs anything.